is here today to talk to us about polarization observations and going to give us a talk. She's a research professor here at the University of Arizona, developing polarimetric instrumentation, polarized light, scattering models, and computer vision and graphics capabilities. She did her bachelor's with the highest honors in imaging technologies from Rochester Institute of Technology. She did her master's and PhD here in the College of Optics. She's got way too many awards for me to describe here, but believe me, it's there's a lot of awards. So with that, I would like to introduce Dr. Kupinski.
Thank you so much, Ron, for the introduction. Thank you for the invitation to give a colloquium at my home institution. It certainly means so much to me to be here today. And when I think about it, it's been a while since I gave a talk that wasn't on Zoom. So it especially feels good to come out from the COVID thaw and be here to talk to you today about cloud observations from cloud emission to Fresnel-dominated scattering. So there's a large breadth of work here in the talk, and it's because we have a large and very diverse group. I joined the college, as Ron said, 12 years ago to work with Professor Russell Chipman. And if a faculty member's job is to see around corners and solve the problems of tomorrow, and today people ask me, well, where are all the female faculty members? Well, Russell was recruiting us 12 years ago, right? And so it is from his mentorship and training that I get to be here today. And I get to graduate my first two PhD students, Kira Shanks and Khalid Omer. They'll be defending next month. And their work is the focus of the presentation today. When I put together, thanks, Russell. We have such a great team at the moment. When I look at all these faces, I think we're also very trauma bonded from COVID. So as you look at all of the work and research that I talk about today, most of it's been performed in the last 2 years during COVID. So that just puts even another spin on it. I think for those of us that always knew research took an incredible amount of resilience, right? In this past 2 years, we deserve a pat on the back, right, for how much we really brought it. And then I'll give an overview of the group. Quinn's a third-year PhD student, and his work is represented here as well. Clarissa and Jacqueline are just getting started, and so when I talk about future projects and outlooks, their work will come up. Jeremy Parkinson is a master's student. He's done an incredible amount of engineering to make our field deployments possible. And Caleb and Caroline are our undergraduate research assistants. As I talk to my colleagues today, student recruitment always comes up, right? And as a professor, even as a research professor, I see myself in the business of talent development. And so having these undergraduate research assistants in the group really helps us get the message out, right? Because they don't need optics, right? These are talented, hardworking, capable people. Optics needs them, right? And that's the recruitment message that I think really wins. So I'm going to start by talking about our IR-CSP instrument. This is our infrared channeled spectral polarimeter. This was designed to measure cirrus ice cloud microphysical properties, and I'll say a little bit more about what I mean by that. So this was part of a submillimeter wave and IR polarimeter, or SWIRP project, that was sponsored by NASA Goddard Space Flight Center. And the PI of that project there, his name is Dong Wu. You really couldn't ask for a better sponsor than Dong. He always talks up U of A, especially how productive we've been, again, during COVID, working through lab shutdowns when we were down to 2 people and signing all of these forms to keep working. And he has other academic partnerships, and so it's really, the students have really brought up the reputation of the University of Arizona to the Earth Science Technology Office through these accomplishments. And so the science goal was to make linear Stokes measurements with 1 micron spectral resolution in the thermal IR. So this is the waveband of 8 to 12 microns. And we had some swaps, some size, weight, and power requirements that I'll talk about. Most notably, it was for a Cubesat application, so we'd like this to fit into 1U, so less than 10 centimeters in length. The thermal IR, all the best detectors, as Professor Driggers talked about in his colloquium, are cooled detectors. In the last 5 to 7 years. There are commercial off-the-shelf uncooled microbolometers, and we use those to fit the swap and form factor requirements, as well as no moving parts. So I'll talk about that technology. So here's something of the timeline of the IRCSP instrument. And so this scientific objective to measure microphysical properties of clouds, specifically ice clouds and faceted geometry of ice crystal structure, and then the engineering approach that we took of spectral-channeled polarimetry. This is an instrument concept that exists in the visible, has a much higher technology readiness level in the visible, has been launched on high altitude aircrafts and so forth. But we are the first to implement it and demonstrate it in the thermal IR. So we'll go through the optical design and some of the software that we did. And I think there I want to make this point about the integration of hardware and software requirements and how you can think about your scientific objective, how you can do your end-to-end modeling, and then how you can ask yourself, trying to, as we always do, work as much as possible with commercial off-the-shelf technology, work with things that are cost efficient, develop these technologies in as rapid as possible period of time, especially when you're doing balloon type of flights, right? The idea is just to demonstrate the technology to motivate more investment in the technology, right? And so we always have this sort of combined, really finite resource sort of Venn diagram. But I want to make the point that you can do some things in hardware and some things in software, right? And this is that end-to-end capabilities approach that merges image science and optical engineering. Then working on the calibration and validation. This is a picture of our, actually this is a picture from Goddard of their test setup. And then last summer doing our first near space deployment on a scientific balloon out of New Mexico. So this is a very complicated picture that goes with a very complicated problem, which is the Earth's energy budget. And when you think about this budget, what you're trying to audit is how much solar radiation is being reflected back up to space, how much is being absorbed in the atmosphere, how much is hitting the Earth, how much of that is reflected and then is upwelling. This accounting is really important for climate models, both for long-term models and even for short-term weather predictions. And so what's circled here is the bubble. It is a little hard to read, about thermal radiation that's emitted by the clouds. So this is a large contributor of uncertainty into the total radiation budget. We also have latent heat processes, and there's atmospheric windows, there's ozone absorption in the thermal IR to consider, but this is a great source of uncertainty, right? And so what's inside the cloud, what it's made of, what are the particle sizes, what type of nucleation process happened, what are the structures of the ice crystal, this all becomes related to the lifetime of the cloud, the probability of the precipitation of the cloud, and is needed for weather forecasting and storm modeling. So this is the scientific motivation for developing the technology. MODIS is a current satellite that's in orbit, and here's just a visible image of some clouds. And so if you were to look at them, you would have no idea, right? If I asked you what is particle size, is it ice cloud, water cloud, some mixed phase cloud, some combination of the two, right? You don't get this in the glance. It looks like a nice, beautiful white cloud, right? And MODIS has data products to estimate what that cloud thermodynamic phase is. And you can see that with the color coding. So here, mixed or unknown is blue, ice clouds are in green, liquid clouds are in the red, and then clear sky conditions. And so this is super interesting, again, to get back to those microphysical properties of the cloud. And so the scientific objective was developing a spectral polarimeter in the thermal IR to better understand this Earth's radiation budget, which I've already said. This picture here is not our simulation in-house, but from a recent 2019 paper which is simulating a brightness temperature difference. And so you see BT is for brightness temperature. This is the units of radiance in the thermal IR. And H is for the horizontal, and V is for the vertical. And so in this picture, we're looking at the difference of horizontal minus vertical. And so if it was an unpolarized signal, we would just get something that was white. And you can kind of see that down the center here. This is the nadir view. Right? So here you just have something white where there's really no polarimetry. But you can see areas of blue, which is more towards vertical, and areas of red, which is more towards a horizontal preference for polarization. And so the question is, this hypothesized polarimetric signal, can it do anything to tell us about the thermodynamic phase, the optical depth of the cloud, and other kinds of information? So here's just a sort of first principled, right, because we want to look at the fundamental physics of the problem. So here's a calculation of polarization-dependent, emission here on the left. And so you can see the emission has a preference towards being vertically polarized. This is why it's a blue color on this particular scale. And in reflection, and this has a preference towards being horizontally polarized, which is why you see that it's red. And of course, as all of the calculations from Fresnel equations, this is highly dependent on scattering geometry and on wavelength. And so that's what fills out this 2D plot. And what we did here on the right is just take one of these uncooled microbolometers and simply put a polarizer in front of it to measure the horizontal-vertical preference of polarization just from a clear sky and a palm tree. And so what you immediately see popping out in the color is that you have reflections here from the sky leading towards the horizontal polarization, and you have emissions from the palm tree leading towards the vertical polarization. And so you immediately, from this preferential orientation of the polarization, you get some idea of what is the dominant process. Am I observing something in reflection or scattering, or am I observing something in emission, right? And so we have the expectation that if you have an optically thin cloud, then you're going to be observing upwelling radiation from the Earth that's going to be creating forward scattering and therefore horizontal polarization. If you have optically thick clouds, you're then not going to be able to, all that upwelling radiation will be absorbed, re-emitted in emission, and you'll have something towards vertical polarization. And so that's kind of a rough way to understand the origin of, in that simulated polarization picture, why you have both horizontal and vertical preferential polarization. And so given that this is the science requirement, and of course I'm just showing you one picture, so this is just showing you this information at one wavelength. If you were doing a radiative transfer calculation that you needed to invert to do these retrievals of microphysical properties, you would want spectrally resolved information, right? Because of course those Fresnel coefficients depend very heavily on wavelength. And so the science goal was 1 micron of resolution in this thermal IR waveband. And so the IRCSP uses channeled spectral polarimetry, and here's the instrument as built. So this was fabricated here on the first floor by Chang Jin's group in the Optical Engineering and Fabrication facility. And I'm just going to step through this optical layout element by element to talk about how channeled spectral polarimetry is performed. So here in the field stop and the collimating optics, imagine that you have, I'm trying to get my pointer to work, there we go. Imagine that you have an incoming field that's linearly polarized coming into this collimated assembly. We then focus down on a field stop that I'll talk about later, and then here in collimated space we have a quarter wave plate and a high order retarder that I'm going to talk about next. It's important for anyone that's taken 586, Polarization and Optical Design. We spend a lot of time talking about how these elements are going to have an angle of incidence dependence, right? So when possible, you put your polarization optics in collimated space. So pay attention to the picture on the right. So just imagine that over this wave band, and of course we're in the thermal IR, but we just always use colors for wavelength because we can't resist, that you have incoming linearly polarized light. And on the bottom here is where I'm building my Mueller Matrix model. So here's my incoming polarized field, then next hitting the quarter wave plate. And the high order retarder. And so that's going to add some ellipticity or some rotation to those linear polarization states as they come out of that quarter wave plate and that high order retarder. And that ellipticity is going to be different depending on the wavelength, right? The magnitude of that retardance is going to be a function of the wavelength. And so as you see, even though all of these colors have the same polarization state going into the instrument, they then have different ellipticities as they exit those polarizing optics. The next thing that happens, we considered a Wollaston prism design. We could not get that fabricated within our cost and time budgets, right? But there are some Wollaston prisms in the thermal IR. Instead, we went with a simple linear polarizer, right? And so this has a transmitted and a reflected path. We definitely lose efficiency with the reflected path, but it's again something that we can account for in the calibration of the instrument. And so as you have these elliptical polarization states hitting the linear polarizer, what you're going to have is a transmission through that linear polarizer that now is highly a function of wavelength. And so you're going to get this frequency here, this expected carrier frequency, that's a function of how we designed our high order retarder. And I'll talk about that next. So this was originally for a Cubesat application. As I said, this is the drum that the instrument was designed to fit inside of. There was 2 other microwave instruments. That Cubesat project has had a lot of delays. But here was our original flow down kind of swap requirements. We had polarimetric precision that was spec'd at 1 Kelvin. Kira and I wrote an entire paper about specifying polarimetric resolution in the thermal IR because there's really a lot to that. It really depends. When you talk about 1 Kelvin, it depends on the strength of your signal, right? On what the temperature is that you're observing, whether or not you can make that, and an NEDT of 1. And so really, if you have to boil it all down to 1, NASA uses TRLs, or technology readiness levels. And the challenge, the big dream, was to advance it from a 3 to a 5 in only a 3-year period of time through this demonstration. We had the limited availability of optics that are available in the thermal IR. So here's the Wollaston prism that we couldn't quite get to. But we did select the uncooled microbolometers, and it was really Donglu out of Goddard that was the catalyst and the champion for dreaming that with this uncooled thermal detector, we could achieve the type of radiometric and polarimetric resolution that would be of scientific value. And so, as I talked about a little bit in the beginning, the concept here is to think about your system end to end, and in which domain? In software, in the way that you design your models, in the way you do your calibrations. Are there things that you can fix? Or are these things that have to be spec'd in the hardware, right? And of course, they have to be spec'd in the hardware. They're usually slightly more expensive. So we think about the polarization aberrations of the lens and collimation error and any kind of retardance error that could be in these elements. Anytime I look at a layout of a polarimeter, there's a point at which the polarization upstream is going to be attributed to the scene that you're observing, and there's a point in which the polarization downstream is not going to matter. It's going to be something that can be handled in calibration and validation. And for us, that point is the linear polarizer. So even though we can expect, for example, some diffraction efficiencies for these gratings that are highly polarization dependent, after the linear polarizer, you have linearly polarized light, right? No matter what hit the instrument. So it's all of the optics before the linear polarizer that are doing the modulation and helping with the retrieval of that signal. So we did have a spec on our retardance error. I'll talk a little bit about that in the next slide. We have this reduced contrast from the linear polarizer. A linear polarizer is by no means a great beam splitter. But again, it was something that we were able to calibrate out for. Drift in the detector response, we do have to calibrate these. We do some onboard calibrations. And pixel pitch and grading dispersion was kind of an interesting limitation to think of. So you have to, once you have some idea of each of these limitations, the idea is in the design process to think about how the final performance is impacted and then adapting, as I say, either the hardware calibration or the data reduction in parallel. And so we did that multiple times over multiple dimensions as we built this polarimeter, but the one I wanted to use as an example, because it exists in all imaging instruments, is a throughput resolution kind of a trade-off. But it was also fun because I remember the day that Kira came in after taking 604, a class that I now teach for applied mathematics and image science, and saying, wow, this really applies to our instrument. Like, we really actually need to think about the finite width of our point spread function of our instrument and account for that as we specify what kind of thickness our crystal should be. So let me kind of walk you through that, right? So the field stop and the dimension of the field stop is going to be what determines, and we have the set pixel pitch. This is the beauty of the uncooled microbolometer, is that the pixel pitch is reduced to now only 17 microns. And so imaging for a long time was not possible with these uncooled thermal detectors until then. But the pixel pitch is something that's set, but we can, of course, control the relative width of the PSF based on the field stop size. The field stop size is then going to control the spectral resolution. So here what I'm plotting is the thickness of the retarder. If I make the retarder thicker and thicker, what's going to be happening to my carrier frequency is that the carrier frequency is going to be having a longer and longer period. So in the slide that I showed previously, right, you come in sort of with a knowledge of what your birefringence is and what your wavelength is, and you say, oh, this is the carrier frequency pattern that I'm looking for when I'm observing a polarized signal. And so here in the idealized case, you can see that that's the same across my waveband. Right? What ends up actually happening in practice is that retardance, as I told you, is a function of wavelength. And then I also have to consider the finite spot size, or PSF, that's dictated by that slit size. And so that carrier frequency is going to be a higher frequency at shorter wavelengths. And so for a given spot size, right, I'm not going to be necessarily sampling that finely enough to resolve that carrier frequency. And so even though I want, even though I want to be, I have to be able to resolve this carrier frequency across my waveband to meet my science requirement. And so we really needed to take into account what that spot size would be so that we could pick the right crystal thickness, right? And so here's a plot of resolvable degree of polarization. So this is something like a Rayleigh task, right, where I say if the degree of polarization is 8%, and that's the smallest difference I can resolve, then I'm up here where my spot size is very large and my crystal is very thick. And then the ideal solution would be to have a very small spot size and a very thick crystal. The very thick crystal would be hard to fabricate. The very small spot size would, of course, lead to throughput issues. But these are the kinds of trade-offs that were important as we specified the hardware. Okay, now I'm going to keep things moving and talk about skipping about 1 year of work from that design phase to the deployment. Jeremy Parkinson led a senior design team that developed this enclosure. And so we had just a set viewing angle. We had a thermoelectric cooler here for our thermal management. We were absolutely petrified of condensation on our optics. So water is completely opaque in the thermal IR. So if we had any condensation on the first optic, we would have taken nothing but dark measurements. We had a PID controller that Professor Fernlid and his postdoc, Maria Ruiz-Gonzalez, helped us with about a week before we left for the flight. So it was all very exciting. And the Salter test flight is in Albuquerque, New Mexico. So we flew here for several hours. The float altitude was 30 kilometers. So this is, just to put it in perspective, about 3 times the altitude of commercial aircraft flights. And we flew just over 100 miles across a lot of desert in New Mexico. What was really exciting about this day, and you can kind of see just even from the picture here, because of the great monsoon activity, we had tons and tons of clouds, right? So as we prepare for our upcoming flights, we can only hope to have such a beautiful cloudy day. So one of the first things that we did just for validation, so in the vernacular of working with NASA, they will always ask for your calibration, your validation, and they will never believe a plot without error bars, right? These are sort of like the tenets of working with NASA engineers. And so one of the things that we learned as we were a piggyback mission and talking to people with other flights is they said, as you go up and up, you just do sort of a sanity check to make sure that, that you can resolve this absorption here in the 9-micron band. And so here as I'm plotting the relative brightness temperature in my 3 wave bands, you sure enough see as the flight goes on and my altitude goes from 5 up to 30 kilometers that I do have this inversion in the brightness temperatures of my wave bands that's indicative of ozone absorption. So that was one of our first just kind of passing the smell test analysis that we did with the flight. And here's my degree of linear polarization in the 3 wave bands. And so there are error bars on this plot, so we did do a lot of significance testing. So as you can imagine, we have this expected carrier frequency based again on the thickness of that high order retarder. And we can do, even with very noisy data sets, statistical significance testing for whether that carrier frequency exists in the measurements. And you can see we have degrees of linear polarization all the way up to 20%, but an awful large population around 5% or so. So the GOES-R instrument retrieves as a data product a kinetic cloud top temperature. And so we wanted to see for these very cloudy conditions, what types of clouds were we looking at. Scientific ballooning is so great for a first pass technology demonstration, but we have absolutely no precision pointing, right? We're just on a balloon which is spinning around. So the yellow circle indicates anywhere that my instrument might be pointed at this period of time. I don't have pointing information. But what's great is to see temperatures here that are indicative certainly of water clouds, potentially of mixed phase clouds, and again in the blue, something that would look closer to an ice cloud. And so when I started talking about this project, you know, it was, can brightness temperature and optical depth be shown to be related to polarimetry in the thermal IR? And we certainly don't have a open and shut case on that yet, but we have some data that makes us feel really excited. So here's my 3 different wave bands again, and showing brightness temperatures where at 270 I'm putting a threshold on the population that's blue for the lower brightness temperatures and the population that's red for the higher. I'm looking at the log in the degree of polarization because again these polarizations do tend to cluster around just a few %. And what's really interesting to see is that both at 9 and 11 especially, which is where I have the most polarimetric sensitivity, I do see a difference in the mean between these 2 populations. So this is potentially indicating that there is a brightness temperature trend in polarimetry that could be useful for inverting cloud microphysical properties. I really like the way that Kira plotted this data. So this is a histogram in DOLP. And for those of us that work in polarization, we always struggle with showing our highly dimensional data because it's not just how polarized it is, it's also what is the orientation. And I explained in the beginning how it's very important if you're more towards vertical, you're in emission. If you're more towards horizontal, you're in reflection. And so what Kira did here is also histogram the orientation. And so the fact that I can see in the 8 and in the 11 a strong preference towards horizontal not only gives me, again, a hint, right? Not a conclusive, but a hint that I'm observing more clouds in reflection than in emission. But also if I was simply observing something that was noise, I would expect I might see a magnitude of DOLP, but I certainly wouldn't see any kind of preferential orientation of polarization. And I like all the head nods that I'm getting from the students that are really strong in polarization. Future perspectives. Jacqueline is a first-year PhD student, and she will be doing our next flight for this technology this coming summer. And so instead of on a balloon, we're going to be on a passenger aircraft. This is a NASA P3. This will be part of the Student Airborne Science Aviation Project. And so Jacqueline has been briefed to please come and teach in our classroom in the sky. So she's going to be putting the instrument on a non-pressurized space at the bottom of this aircraft and interacting with students and talking about what it's like to work in polarimetry, what it's like to be in Arizona. And we're all very excited. So she'll do, not just the fun part, but also a lot of the integration and assembly for that field deployment. It's going to be a lot of work, but we're super excited. And we have a commitment to fly this technology for the next 4 summers. We're going to do another balloon flight, and Jeremy's been doing a lot of the engineering. We also, again, the point of demonstrating this technology was to get more investment, so now we can afford to work again with Changjin Yu and the Optical Engineering Fabrication Facility. So we're going to pressurize our instrument. We're going to have improved thermal management. We're going to keep our focal plane a lot colder. So we're going to have much better statistics on these very polarized, but only very slightly, right? Only under 5% normally polarized signals. Carissa DeLeon is a second-year PhD student, and her and I are also working in the realm of polarimetry for atmospheric studies, but in a different waveband. So she's developed an instrument in the ultraviolet, and she's here just on the roof of my now taking some validation measurements of clear sky conditions. And her and I had the idea. We have actually passed we've been invited for full proposal after an initial NASA proposal where we said, you always rotate the retarder. What if we just slap a retarder on the UAV and let the UAV fly around all crazy? And what if we do this in front of something very homogeneous, like wildfire smoke, right? And so I think of this as like a very highly non-rectilinear sampling of polarimetry. But again, thinking about like if we can move the requirements of retrieving those microphysical properties from the hardware domain, right, into the software domain and through retrievals and calibration and forward modeling, and get this job done with simpler hardware. And so, again, Russell and myself 12 years ago, I kind of cut my teeth on multi-angle polarimetry for aerosol science. And this is being launched into space satellites currently, and very high precision technology in the visible is upcoming with the Maya project. And so multi-angle polarimetry in general has absolutely proven itself in the aerosol community. And this idea is to do it instead in the ultraviolet, where you have aerosols with carbon concentration that are very highly absorbing, and to do it for tasks related to wildfire science. Now I'm going to shift gears completely away from the atmospheric sciences part of the talk and into computer vision and graphics. And so instead of radiative transfer and thinking about emissions and thermal IR and scattering, we are back down on Earth and just thinking about very simple polarized BRDF, bireflection, distribution, function types of models. And so when you look at many of these are incredibly simple models where they say you have some contributions from specular reflection that can be quantified by Fresnel reflection. And then you're going to have some things that penetrate into the material, have some subsurface scattering, and refract back out. And these can potentially be partially polarized, but sometimes not very polarized at all. And then when you're in off-specular configurations, microfacet models postulate that there's simply little sub-resolution mirrors, right, that are still contributing Fresnel reflection, even in off-specular geometries. And so when you look at these very simple models, we asked ourselves the question, if the models are simple, can we make really simple measurements that just directly get at the parameters of these models? So again, trying to use very simple hardware to solve very complicated problems. And a former PhD student who's now doing her postdoc at Harvard, Lisa Lee, and I wrote a paper on this topic last year. So here's a look into the lab at our Mueller Matrix movie studio. Kirby is like a little cartoon type character. I'm not much of a gamer, but I see some of the gamers smiling, right? So here is Kirby, and he's getting his Mueller Matrix picture taken, right, at all different kinds of angles in the goniometer. This is a rotating retarder polarimeter, and so the graphic here is just showing the rotation of the fast axis of those two purple elements that are the retarders. And as these rotate, we think of that tracing out a polarization state on the Poincare sphere that follows a figure-8 trajectory. So that's what's happening in the lower right-hand corner. And so you build up a linear system that you then invert to solve for a Mueller matrix that has 16 elements, right, and kind of looks like this. This instrument absolutely has really unique capabilities in that we have a very large area source. It's what's behind Kirby's head. We're measuring in 4 visible and a 950 wavelength with a very high dynamic range camera. I mean, polarimetry is nothing but multidimensional radiometry, right? But you need to be careful not to under and oversaturate, right, in that higher polarimetric dimension. So you typically do need very high dynamic range. And in a 14-degree field of view, so we can do things kind of more interesting. So we make a lot of measurements, but we sure would love to make less. And so here is showing just a pink sphere. And you measure a sphere in computer graphics, right, so that in one snapshot you can get several different scattering geometries. And so on the left-hand side is the full Mueller matrix measurement, and on the right-hand side is a model that we developed that kind of goes with this simplified microfacet Fresnel-dominated type of scattering model we call a triple degenerate assumption. So this compresses by a factor of 2, so you need only 8 parameters to get to the Mueller matrix on the right, and at least by visual inspection, they sure do look pretty close to one another, right? Maybe not the precision that you would need for a NASA aerosol application, right? But perhaps sufficient precision for computer vision and graphics. And so this triply degenerate assumption is pretty cool. And what it allows us to do in the context of rendering is introduce the idea of importance sampling in the polarimetric domain. So importance sampling is always done in ray traces when you're back propagating from the detector to the light source and using the BRDF, right, to sample your ray geometries, right? You don't sample those ray geometries uniformly. You use information about the material and its BRDF function. And what our modeling is showing is introducing the idea of also doing polarimetric importance sampling. So you can think about, for each individual ray interaction, making a selection between an ensemble of Mueller matrices, propagating that through to the detector, and then doing incoherent addition or averaging of rays at the detector plane to get your ensemble response. Now, the reason this is really exciting is because you could potentially do this in a Jones formalism with completely non-depolarizing interactions and then account for all of your depolarization at the detector plane. That would, again, have a lot of computational advantages in terms of a reduced parameterization. And so the probability would look something like this. Instead of plugging my Mueller matrix in to my rendering, I would plug in something with probabilities. And so then I would do selections at each ray interaction. So you could think about a ray coming in and sampling a probability to either calculate a Fresnel reflection using a microfacet theory, or just consider only radiometry. Consider that it's an ideal depolarizer, and no matter what hits it, it's completely unpolarized going out. And so these probabilities are then going to become how you characterize the polarization properties of the materials. And they're going to depend on scattering geometry, they're going to depend on albedo, they're going to depend on surface texture. But it's a low-dimensional parameterization compared to that full Mueller matrix measurement. This is the work of Quinn Jarecki, and he'll be presenting this at an SPIE conference next month. And so here he's using a commercial off-the-shelf linear Stokes camera, which, if you're not familiar with these, very much like our RGB cameras, mosaic the focal plane in a Bayer pattern. This type of camera created by Sony mosaics the focal plane with polarizing filters at different orientations. And so in doing so, just in one snapshot, you can get 4 linear measurements. And so we created this sample here that's just simply blue Lego bricks, and we imparted different textures just through the way these were sanded and treated. And RA values are just a way to quantify the surface texture of these objects, because the surface texture does indeed affect the polarimetry. And so what we have here on the left are the 40 measurements made in the Mueller Matrix studio, and this will play just over my geometries. So on the left is my full Mueller matrix characterization, and on the right are simply the 4 measurements made just with the lucid camera, right? And so for this blue plastic piece with several different surface textures, again, you see that a lot of the dominant polarization properties have been retained. And so this was an exciting result for us. We also look at the depolarization structure as what's on the diagonal of this matrix. And so you can see a lot of that pattern or trend with surface texture is retained in the 4 measurements versus the 40. Okay, and now I'll switch to talking about, that's more sort of like computer vision and partial polarimetry. And Khalid Omar is working on physically based rendering and bringing polarization into computer graphics and into rendering. So rendering is a very advanced field where you can hardly tell the difference between something rendered and a real photograph. Nowadays, there's so much photorealism. They do this by mimicking light-matter interaction in ways that are very physically plausible, but most of the time polarization is not considered, right? And there is interest in getting more photorealism, especially, of course, around speculars and other things using polarization. And so in path tracers, and maybe I could have shown this picture first to give you guys a better idea about polarimetric importance sampling, right? But all of these, when we think about graphics, these really are the ray traces that we're familiar with. They just don't keep track of absolute phase the way we have to in optical design, right? But we're still launching rays all over the place, and usually doing so in a Monte Carlo type of simulation where these ray directions are importance sampled. And so again, this is just showing the different BRDF functions and the ways those would be built up by multiple ray interactions. And your number of samples per pixel, or SPP, will report next. And so, of course, as you increase your SPP, you get a better looking image, right, with less variation. And so in a typical PBR pipeline, you start with some kind of like STL or triangulated description of the geometry of your scene. You can have, in general, very complicated lighting scenarios, as you'll see in some of the renderings, right? But multiple light sources, multiple sort of ray depths, shadows and penumbras of shadows. And then your material properties, which are specified by your bidirectional, either scattering or reflection is used here, right, for your BRDF. And then your camera properties to get radiometric renderings. And so the way this pipeline changes is for a polarized PBRDF pipeline. You still have your geometry, you still have your lighting, but we now need a polarized BRDF that's in general going to be Mueller matrix valued at all of your scattering geometries. And you need, instead of just a camera, to have some kind of a polarimeter or a Stokes camera there. So that then, instead of just your radiometric picture, you can get your full Stokes parameter descriptions. So for this project, we used a physically based renderer that does offer some polarization capabilities. This is very much a research grade ray trace engine. So we were something of like the alpha users. I think we really participated in the refinement of this tool. And it did allow us to import kind of customized PBRDFs, right? So that measurements we were making in the lab, we could import into this Mitsuba 2 rendering tool. And so this KAIST PBRDF database is what we'll be using in the renderings, and they took spheres of 25 different samples. They tried to cover different metallics and diffuse different colors to get a good ensemble look or a good representational sort of materials with which to do renderings. What you see in Mueller Matrix polarimetry, really in all polarimetry, is that noise can move you out of the physical realm of reconstructions. And since a lot of my 637 students are here, right, if your measurements aren't in consistency space, right, then yeah, then you can, you can through these pseudo-inverse reconstructions, have some non-physical solutions. And one advantage of our model is that it takes care of that. So again, back to the triply degenerate assumption, and you know, I've been doing this too long to know that you don't want to see an equation. But just suffice it to say that, again, we have a 2x factor of compression using this model. We're also able to impart this physical constraint, so that we're always going to have physical Stokes parameters coming in and going out. This becomes really important because when you specify your polarized BRDF, you don't do so at all geometries, right? And so part of the ray trace is interpolating to the unmeasured geometries that become sampled in the course of the Monte Carlo ray trace. So again, here's a rendering of a sphere, and we used the KAIST PBRDF models here just to render up a pink sphere. Right here's where they have some trouble with some of their non-physical solutions. And here's our Mueller Matrix model with the 2x compression, as well as with the physical constraint imposed. And so here's the same triply degenerate Mueller matrix on the left, and then on the right I'm implementing the polarimetric importance sampling that I talked about. And so it's a little bit of like a difficult result to get an audience excited about because it looks exactly the same, like maybe I just made a copy-paste error, but that's of course exactly what I want, right? Because the picture on the right was computed in a fundamentally different way that offers a lot of advantages. And so here's what these renderings look like over a more complicated scene. And so in computer graphics, they are really, really good at coming up with these, fun little figurines to measure. So here we have the robots. If you look at a picture like this and think about the Monte Carlo ray trace I showed, where you have all the rays zinging around and interacting before they come back to the detector, this is called the number of interactions in between emission and the detector is like the ray depth. And so when you're in shadows, you have a larger ray depth, for example. And so you can see here for the original model and for the triply degenerate model, an awful lot of resemblance in the angle of linear polarization. The angle is just going between 0 and 180 degrees on this color scale that tries to wrap, right? Because there's a lot of people in the polarization class. Polarization is not a vector direction, it's an orientation, right? So 0 and 180 are the same. So we wrap the color bar. And up top here we have the degree of linear polarization. And this is all in the red band, right, Colin? Yeah, this is all in the red band. And so one of the things that you do, one of the things that's kind of fun to share, is to think about, you always need kind of a smell test, right, to look at your results. You go, oh, I got these new results, are they correct? And so a first principled approach for polarimetry is to think about UMOV's result. And so this relates the albedo of a material to what you expect in its degree of polarization. And so it's very simple. If you think about something that's very dark, right, it's much more likely that its excidence is going to just have one first surface reflection as compared to something that's very high albedo where you can expect more multiple interactions that will be depolarizing. right? And so what we see here measured in a red band is things that are pink, like the legs of the robot, then are going to have a very low polarization, right? And then things that are very blue here, I think it's more like the blue, right? Because the blue should be, well, I wonder if this is the red channel, in fact, comment. Because, yeah, I think this is, in fact, that's what I get for trying to be extemporaneous. Yeah, I'm not sure this trends with the red channel, so I should check. Because UMOB's effect is the smell test, right? So if I have something dark, you know, the seats here, I'm expecting a higher degree of polarization as compared to something with high albedo that's going to have more multiple interacting effects. And so this is comparing, again, the original. The middle is our triple degenerate approximation, factor of 2, physically realizable. And then on the far right with the polarimetric importance sampling. And so this is a scene that has a pretty complicated illumination because the light is just coming through a door that's ajar. And so there's no direct illumination onto the table, into the teapots and so forth. And so on the left is showing the original. On the middle is showing our triply degenerate approximation, and then our probabilistic implementation. And so you certainly see where the ray depth is high, where it's deep in the shadows. You definitely see more noise, as expected for the probabilistic interpretation, or computation, I should say. But again, a lot of similarities and a lot of computational advantages. So I'll just kind of end by, I guess, trying to summarize my outlook and the points I tried to hit throughout the talk. I think what's really special about the curriculum here in our college is that we combined our expertise in optical engineering and image science. This is such an important part of our student training. In talking to many of my colleagues today, I know that in other programs, or you can sort of come in and people can say, oh, nice to meet you, you're 22 years old and smart. Are you a theoretician or an experimentalist? Please decide, right? And I hear the students kind of nodding. And you know, even though most of us throughout our career might say we're stronger in one of these areas than another, it truly is important, right, to be somewhat proficient in both. And I think as the students look at the projects that are most exciting, right, have some challenging computational element to them and some challenging instrumentational element to them as well. And so this idea of doing a very short timeline and low-cost technology development, I think is where you can really see that you have to be someone that can look on the continuum of your solution space, right? Like what jobs can I get done in hardware? What jobs can I sort of compensate for in software, right? If some of my hardware specs are not so great, can I make up for this with very clever software solutions? And so doing these types of demonstrations is what, at least in the context of you know, moving something up the TRL ladder, to motivate further investment is super important. And then the last part of my talk in the realm of computer vision and graphics, I feel like there I really have to take responsibility to say, polarization, now anybody can measure it, right? And so how can we use our expertise and our mastery to really push the applications for what that makes possible, right? And I don't think that's throwing it all into a convolutional neural net. Although I love convolutional neural nets, right, and they're right for some jobs, right, I think that really using that optical and physics-based approach to the modeling is how we're going to be able to extract every little drop of useful information out of this partial low-cost polarimetry. And then I just want to end with the University of Arizona land use statement, and in front of this audience just affirm my commitment to training the future leaders in optics. This is absolutely how I see my job in a day-to-day way. And I remember being recruited by Russell for his group, and he's such an ace at student recruitment, right? And the message I remember that resonated with me was not, oh, you need optics, and if you're good enough, you can survive, right? Optics needs you guys, right? And the leaders in optics are going to have all of the faces of diversity, right? Women and Hispanic and Black and international, and our field needs absolutely as much talent as it can get. So optics needs you guys, and I'm in the business of training the best people in the world in optics. So thank you so much for your time and attention. I really appreciate it.
Are there any questions for Dr. Kupinski?
Meredith, I see that with spectroscopy you can measure the properties of materials. You can identify different compounds, for example. You can do Doppler spectroscopy to find velocity of objects. You can do itosometry with polarization to measure thickness and refractive index of thin films. What kind of information are you getting from this kind of polarimetry that you cannot get otherwise using photography, spectroscopy, velocimetry, and things like that?
For the atmospheric science application, or for all of them?
In general, when you do
Yeah.
polarimetry, the type of things that you described, what kind of information are you getting that is not available to you with other techniques?
So, for example, in the atmospheric application, I haven't seen it possible to get particle size, right, or shape from spectroscopy. That's only partially true because, as you said, you can do speciation, right? And so from speciation, you could know these molecular attributes, right? But there's a great sensitivity in polarization to particle shape and size in the atmosphere. It's also a passive technology, and so that has just a great advantage, right? And so I think it's, in the realm of ellipsometry and characterizing thin films, polarimetry is possible. I don't know that you can put polarimetry up against, technologies when you include something active, right, or a detector that's cooled, or, but I think the advantages come in when you think about a technology in particular that's passive.
Any other questions?
So I think when you were talking about Clarissa's project with transferring some sort of application from hardware to software with like a retarder plate or something like that.
Yeah.
And so initially it seemed to me like you were going to use wildfires because they provided this kind of homogeneous environment to measure on. But then towards the end of that it sounded like, oh, we can learn some interesting things about wildfires. I was just curious about the motivation there, which direction that goes in.
Yeah, so that's a project that's just getting off the ground. Some of the applications that we're targeting are aging the wildfire smoke, right? So as it propagates and as you think about measuring the fire close to ignition, a few days from the ignition, again, you can have a lot of the carbon concentration changing, the albedo is changing, some of the shapes of the particles are changing, especially as they mix in the atmosphere. So those are some of the applications that we're looking at. You're right that it's important that it's homogeneous if you're just going to fly a drone in some crazy pattern over the smoke, right? But again, that would be something that you could assume some kind of distance over which you had homogeneity, right? And so even on like a longer flight, right, you could still process the data and not assume over the whole flight it was homogeneous, right? But use like GPS location or something, right, to make a homogeneous assumption.
I've got a question. In the Army, there's a high interest in seeing through degraded visual environments like dust and smoke and fog and haze and those. Is there any opportunity with polarization for assisting being able to see through?
Yeah, so dehazing in polarimetry is like an application that's a few decades old, right? And Yoav Shechner out of Israel, I think, has really pioneered the field of dehazing with polarimetry. And more or less based on the idea, right, that with multiple scattering, right, you have a degree of polarization that's decreasing, right? And so if you keep only the polarized portion of the signal, you can do some dehazing.
Thanks. There was one question.
I've also seen cases where camouflaged objects do not look camouflaged when they're captured with polarization.
Yeah. The one in the thermal IR that's fun is the disturbed Earth, right? Problem with polarization. And it's related to the same thing to the surface texture in the Legos, right? It's kind of the same sort of idea. This idea that you have sub-resolution microfacets that are Fresnel scattering, but the distribution of those is going to be a function of the macroscopic surface texture.
There was one question over here. Yes.
For the atmospheric applications, I think you mentioned there were, this isn't my field, so I'm sorry, but I think you mentioned that there were similar devices in the visible, and I was wondering kind of what advantages you were hoping to see from IR and if your preliminary results are kind of showing that.
Right, so the technology for observing polarization from space is currently happening in the visible, and even new instruments with even better polarimetric accuracy, right, are going up very soon. And so they're sensing things like speciation of different types of aerosols, right, and other climate models for that radiation budget. But they're not working in the thermal IR, right? And so the thermal IR will still remain a source of uncertainty in that overall budget, right, until we have instrumentation to measure it. And the ice structure of the crystals, this is like about 20 to 200 microns. And so we also have capabilities in the thermal IR to measure those geometries that we couldn't do in the visible.
All right, let's thank our speaker. Thank you all for coming.